All right, so we started talking about vectors in section 12.2, and now what we're going to do is we're going to take a look at what's called the dot product. We've so far added and subtracted vectors. We've taken scalar multiples of vectors. The next natural question might be, can we multiply two vectors together? Now, in the traditional sense of, let's say I wanted to take the vectors 1, 2, 3 and multiply them by another vector 4, 5, 6, like that. Sadly, we're not just going to multiply component by component. We can't just do 1 times 4 and get 4, 2 times 5 and get 10, 3 times 6 and get 18. It doesn't work the same way as it did with addition and subtraction. So if you wrote that down, put a big X through that. So that's the bad news. The good news is we still have a type of product we can take, and it's called the dot product. And the way it works, and we'll talk about the geometric significance of it in a little bit. The way the dot product works is, say you have two vectors. They might be in R3, they might be in R2. The formula is going to work out the same way. Let's just, for the sake of the definition, let's say we're dealing with two three-dimensional vectors, two vectors that live in R3. We'll call the first one A, we'll call the first one B with given components. The dot product of A and B, denoted A dot B, note these are bolded. So these are both vectors. If I was writing them on paper, I would make sure to put my arrows above them. The dot product, what it is it takes in two vectors, and what it spits out is the sum of the products of the components. So if you notice what's going on here, you can see a pattern. We're taking the product of the first components, A1 and B1. We're taking the product of the second components, A2 and B2. And we're taking the product of the third components, A3 and B3. And then we're summing them together. So what's interesting is that it takes in two vectors. These are both vectors. But this product, sum of products that it spits out, is a scalar. Okay? So the dot product is not a vector. The dot product is a scalar. Okay? Sometimes it's called the scalar product, or you might hear it be called the inner product. Especially if you ever take a linear algebra class, they like to call it an inner product. And vector from Despicable Me here is reminding you that when you take the dot product of two vectors, you just got unvectored because it spits out a scalar. LOL. Okay, so let's evaluate. Let's just do one for practice. Let's say that you're taking the dot product of I plus 2j minus 3k. So in other words, I'm going to do this in component form. 1, 2, negative 3. And we're going to take the dot product of that vector with 2j minus k. So the I component is 0, the j component is 2, and the k component is negative 1. So all we're going to do is we're going to multiply the components together piece by piece, and we're going to take the sum of those products. 1 times 0 plus 2 times 2 plus negative 3 or minus 3 times negative 1 would be 0 plus 4 plus 3 would give us a dot product of 7. It's pretty quick to compute. Some properties of the dot product, and we're going to prove a couple of these. If you take the dot product of a vector with itself, it actually spits out the magnitude of the vector squared. I'm going to put a star by this one. We're going to prove this one in a minute. The dot product is commutative. If you take the dot product of A times B, or A dot B, you're going to get the exact same result as B dot A. So I'm just going to put the property here. The dot product is commutative. The dot product is distributive. If you take the dot product of A and B plus C, it's the same as taking the dot product of A and B and adding the dot product of A and C. So it's a distributive property. It's associative. You can see how they moved the scalar inside and outside the parentheses here. So where you place that scalar will not affect the result. It's associative. And this one shouldn't be too shocking. If you take the dot product of the zero vector and any non-zero vector A, you will always get the scalar 0. One point I want to make in this one is that this is a vector 0. This is the scalar 0. So this is I guess I'd call this an identity. Okay. Let's prove property 1 and property 3. Okay, so in the first one, I want to prove that A dotted with itself is the magnitude of A squared. So all of these, I'm going to start by defining a vector. Let's let A, and we're going to do this in R3. You could prove this in R2 in the same way with just two components. So let's let A be A1, A2, A3, where those are real numbers. And the way that these are going to work is you're going to either start with the left side or the right side, and you need to make the other side show up after some algebraic manipulation. So your goal is to make the left-hand side equal the right-hand side. And it does not matter what side you start with. I'm going to start with the left-hand side because it's, to me, easier to manipulate the dot product and make, the square root show up that we're going to need. Because what is magnitude of A, right? Magnitude of A is going to be A1 squared plus A2 squared plus A3 squared. So if I square that, my goal, this is my goal, is I want A1 squared plus A2 squared plus A3 squared to appear. It looks like a sum of products, so it's probably going to be easier for me to start with the dot product. So I'm going to compute A dot A. That would be A1, A2, A3, dotted with A1, A2, A3. And using our dot product formula, I'm going to get A1 times A1 would be A1 squared, plus A2 times A2 would be A2 squared, plus A3 times A3 would be A3 squared. But that's exactly A1 rad A1 squared plus A2 squared plus A3 squared, all squared. But that's the magnitude of A squared, and that's the right-hand side that we wanted. So that completes our proof. Okay. Hey, let's do one more. In property 3, what do we want to show? We want to show that A dotted with B plus C, this is our goal, is equal to A dotted with B plus A dotted with C. So I'm going to define three vectors. I'm going to let A be A1, A2, A3. I'm going to let B be B1, B2, B3. Oop, not B cubed. My bad. 3. And I'm going to let C be C1, C2, C3. Okay. Got to define your vectors. All right, and again, like we did in the last one, I'm going to start with, I think for me, it'd be easier to start with the left-hand side, and I'm going to try to manipulate it so that it becomes the right-hand side. So I'm going to start with A dotted with B plus C, and we'll see what happens. So A dotted with B plus C. And the thing with these proofs is they're a little tedious. You got to write out each step. You can't make jumps because the reader needs to see what you're doing line by line. So A, there's our vector A, dotted with, I'm going to use brackets here, B1, B2, B3, plus C1, C2, C3. So just expanding out what A, B, and C are. And now what I can do is I can do vector addition with the components of these two vectors. So this is going to be A1, A2, A3 dotted with, and now we're going to have B1 plus C1, B2 plus C2, B3 plus C3. And now I have two vectors. Now I can take the dot product of those two vectors. So I'm going to take the sum of the products of the components. So A1 times B1 plus C1 plus A2 times B2 plus C2 plus A3 times B3 plus C3. And maybe you're wondering, well, how do I know, where am I going with this? My goal is I want to create kind of two separate sets of vectors, one that only uses A and B and another that only uses A and C. And right now my A's and B's and C's are all lumped together. So my next natural step would be to distribute so that I can start getting separate terms that have A's and B's and other separate terms that have A's and C's. That's really what's going to make this right-hand side show up. So kind of trust the process. And things kind of nicely start to work out once you distribute. So I distribute A2, A1, and A3 to each of these. So just normal distributive property like we would do with numbers or variables. And now addition is commutative, so I can reverse the order of any of these terms that I want. I'm going to locate all the terms that have A's and B's, and I'm going to box those in blue. So I'm going to put those together. So A1, B1, right? I can move the order of the addition around. It's just numbers. A2, B2 plus A3, B3. And in green, I'm going to do the other ones. Anything with A's and C's, I'm going to combine together and group together. Plus A1, C1 plus A2, C2 plus A3, C3. And now I'm going to go back to my highlights. What I highlighted in yellow up at the top here, this is A dot B. That's the sum of the products of the components of vectors A and vectors A and B. So this would be A dot B. Plus, in blue, I had highlighted A dot C, but that's exactly what we have left here. This is the sum of the products of the components of the vectors of A and C. So A1, C1 plus A2, C2 plus A3, C3 is exactly A dot C. And that was the goal. That was the right-hand side we wanted. That's it. Okay. I mentioned there was a geometric interpretation of the dot product. A couple ways you can think about it. So really, it's a way of measuring kind of how closely the two vectors that you're looking at point in the same direction. So it's a way to quantify how much they lie on top of each other, or what type of angle they have between them. You could also think of it as a measure of how perpendicular the two vectors are. We'll see in a little bit. There's a special value that always comes out when the two vectors are perpendicular to each other. So think of it as a measure of how closely the two vectors lie next to each other, how perpendicular they are. Okay. So if we define this angle theta between the two vectors, and so you can see in the picture here, it's this angle that sits between vectors A and B here. Okay. We're going to let theta go between 0 and pi. So we're always going to have it be an angle between 0 and 180 degrees. So 0 would be if they both pointed in the same direction. So let's say this was A and this was B. That would be an angle of 0. And then if they pointed in opposite directions, length doesn't matter. This would be theta equals pi. Okay. And so then anything in between, we're going to find a way to measure that now. So one of our first big theorems from this section says that if theta is the angle between vectors A and B, the dot product, here's another way of defining it, the dot product of two vectors A and B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the vectors. And a corollary to this theorem, if you divide over magnitude A times magnitude B to the left-hand side, then we end up with a version that isolates the cosine of theta. This is the one that I usually go to. The cosine of the angle between the two vectors A and B is equal to the dot product of the two vectors divided by the product of their magnitudes. And then to solve for the angle, we would just take the inverse cosine of both sides. So let's try that. What's nice about this is you don't actually have to graph the vectors at all. Okay, so let's find the angle between vector u and vector v. There's the components given. So writing out my formula. Oh, also I wanted to mention, if you're interested in seeing the proof of this is in your text, and it uses the law of cosines. So if you are interested in seeing how this is derived, I'm not going to do this in the notes here, but you can take a look at your textbook and they go through the proof. Find the angle between u and v. Okay, so cosine, let's let the angle be theta, of theta is going to be the dot product of u and v divided by the magnitude of u times the magnitude of v. And you can compute these within the formula, or if you want to do some of your algebra off to the side, it doesn't matter to me, just stay organized. So if I do u dotted with v, I'm going to get 1 times -3 minus 2 times 6 plus 2 times 2, taking the sum of those products of the components of the vectors. The magnitude of u, I'm going to do up here, magnitude of u is going to be 1 squared is 1, plus negative 2 squared is 4, plus 2 squared is 4, so we get square root of 9, which is 3, times magnitude of v is going to be square root of negative 3 squared is going to be 9, plus squared is, or plus 6 squared is 36, plus 2 squared is 4, so we get rad 49, which is 7. And so we end up with, let's see, negative 3 minus 12 would be negative 15, plus 4 would be negative 11 over 21. And so we get that cosine of theta is equal to negative 11 over 21. They asked for the actual angle, so we're going to take the inverse cosine. Did not specify radians or degrees. So if it doesn't specify, feel free to give either. On a quiz or test, I'll specify what I want. So this would be, if you put it in your calculator, about 121.6 degrees, or if you're doing this in radians, you get 2.12 radians. So this one comes out to an obtuse angle, and we can actually use the dot product to help us decide if the angle is going to be acute, if it's going to be obtuse, or if it's going to be right. And really all you need to focus on is the numerator. The denominator here is always going to be positive, since the magnitude of u is always positive and the magnitude of v is always positive. So really, it's all about the numerator. If the numerator ends up being positive, if that dot product is positive, well, then your cosine of your angle is going to be positive. That means the angle has to come from quadrant 1, which means your angle is going to have to be acute. This is since cosine of theta is going to have to be greater than 0. In the second case, if the dot product is negative, well, now you have a negative numerator and a positive denominator. That means cosine is going to have to be negative. Since theta has to be between 0 and pi, or 0 and 180, we know that we're in quadrant 2. So I'm just going to make a note here, quadrant 1. Quadrant 2, assuming that we're dealing with 2-dimensional vectors. If it's 3-dimensional, we're dealing with octants, but you can think about it the same way. Well, if we're in quadrant 2, now we have an obtuse angle. And so this is since cosine of theta is less than 0. It only leaves one more case. What if the dot product is equal to 0? Well, then your numerator would be 0. Your denominator is positive. So you'd have cosine theta equals 0. Well, that only happens when theta is 90 degrees, or pi over 2. Okay, so that would mean that you have to be dealing with a right angle, since cosine of theta is equal to 0. And in the third case, we have a vocab word we need to know for this. We say that the vectors are perpendicular from geometry class. That makes sense. But in the calculus sense, we have a kind of more fancy term we use, and that is the term orthogonal. So if you hear me say orthogonal vectors, that means that their dot product is 0. We have a theorem that says two vectors, A and B, are orthogonal if and only if. It's a biconditional statement. They are orthogonal if and only if their dot product is equal to 0. So what that means is that both directions of the conditional have to be true. If you know the vectors are orthogonal, then you know their dot product has to be 0, and the converse also has to be true. If you know two vectors have a dot product of 0, then those vectors must be orthogonal to each other. Okay. We also can look at vectors that are parallel. So in the special case when theta is 0 or theta is pi, our formula reduces to one of these two cases. And you'll notice that means that each vector is really just a scalar multiple of the other. And so this is the case when the two vectors are parallel to each other. So either vector can be expressed as a scalar multiple of the other vector. Okay. And I kind of drew this on the last page, right? So in the case where theta is equal to 0, they point in the same direction. In the case where theta is equal to pi, they point in the opposite direction, but they still make a straight line. So we can think again of the dot product as measuring the extent to which two vectors point in the same direction. Or if you want to think of it as a measure of how perpendicular they are. It's kind of the best geometric interpretation we can come up with. So some problems might ask you to verify or show that two vectors are orthogonal to each other, in which case you have to go into the problem with a plan. If you're going to show two vectors are orthogonal, it means your goal is going to be to show that their dot product is 0. So as long as we can show that dot product is 0, we're done. All right, so in this case, I'm going to have 2 times 5 plus 2 times -4 minus 1 times 2. So I get 10 minus 8 minus 2. 2 minus 2 is 0. Okay. So I'm just going to conclude by writing, therefore, A and B are orthogonal to each other. Sometimes they might not tell you if they're orthogonal or parallel or neither. You might have to decide. So let's say you have two vectors W and V with given components. We want to decide, are they parallel, are they perpendicular, or neither? Perpendicular, remember, meaning the same thing as orthogonal. Well, you have to kind of, again, go in with a plan. If they're parallel to each other, that means that one vector is going to be a scalar multiple of the other vector for some real number C. C being a real number is what that notation means. If they're perpendicular, that means that their dot product is going to be 0. And if both of these fail, well, then it's neither. I would probably check perpendicular first. It's pretty easy to check the dot product right away and rule that out. So let's check the dot product. If I take W dotted with V, I get 9 times 6 plus 6 times 4 plus 3 times 2. Clearly all positives, non-zero. This is 84 if you do the math. Okay, so that's not 0. So what that tells me is that these vectors are not orthogonal to each other. Perpendicular. Okay. Are they parallel? Well, we need to check. Let's check parallel. If they're parallel, that means I can find some C value, some real number, such that when I multiply the vector V by that scalar, I always get, I'll get W. So you got to go one component at a time. It has to be the same scalar for each component. So that would mean really 3 things I have to check. I would need 9 to equal 6 times C. I would need 6 to equal 4 times C. And I would need 3 to equal 2 times C. And I just need to check to make sure I get the same C value for each component. So in the first one, I get C equals 9 over 6. Let's see. Yeah, so in this case, I would get 3/2. In the second case, 6/4, I would get 3/2. And in the third case, I would get 3 over 2. I would get 3/2. Okay. So I get the same scalar for each one. So since W is equal to 3/2 times V, we conclude that W, make sure you put your arrows above your vectors, W and V are parallel. And if we got a different scalar for these 3 components, well, then we would say that they're neither, because we already ruled out that they're not orthogonal, they're not perpendicular. So that's how to attack one of these problems. Okay, next up. Direction angles and direction cosines. This concept will only make sense if you are dealing with 3-dimensional vectors. So I'm going to say only for R3. The direction angles of a non-zero vector A are the angles, these are Greek letters, alpha, beta, and gamma, all between 0 and pi. That vector A, sketched below here, you can see it in green that I'm overlapping. make with the positive x, y, and z axes respectively. Okay, so really what that means is that alpha is the angle between the positive x-axis and your vector A. Beta is your angle between the positive y-axis and the vector A. And gamma is the angle between the positive z-axis and the angle A. So the one that I have outlined in red is alpha. The one I have outlined in green is beta. And the one I have outlined in green or in pink is gamma. And if you only take the cosine of these angles, then it's called the direction cosine of the vector. How do we find them? Well, think about, we have a way of finding the cosine of the angle between two vectors, right? It's a dot b over magnitude A times magnitude B. Well, they gave us one vector A. If you can create a vector that points in the direction of the x-axis, the y-axis, and the z-axis, you can use what you already know in terms of this formula. Well, what's a vector I know that points in the direction of the x-axis? 1, 0, 0, which is I. What's a vector that I know that points in the direction of the positive y-axis? 0, 1, 0. That's J. How about in the direction of the z-axis? 0, 0, 1. That's K. So all I'm going to do, I'm just scaling down the axes to make them unit vectors, and I'm using those standard basis vectors to accomplish that. So if I want the cosine of alpha, that's going to be the angle it makes with the x-axis. I'm going to take the dot product of A and I divided by the magnitude of A times the magnitude of I. And so this will give me, if I let vector A be A1, A2, A3, let's just, yeah, let's make sure we mention that. A is A1, A2, A3. I is 1, 0, 0. The magnitude of A, we don't really know what A is, so we're just going to leave it like that. The magnitude of I, this is where you have to know your definitions. This is a unit vector, so the magnitude of I would be 1. And so I'm going to get A1 times 1. A2 times 0 will go away. A3 times 0 will go away. So I just get A1 over the magnitude of A. And you could go through the same computation here. This time we're going to use J since we're using the y-axis now. Magnitude of A times magnitude of J. This time the first and third components are going to disappear and you're just going to be left with A2. Same as last time, magnitude of J is a unit vector, or J is a unit vector, so magnitude would be 1. So this time we get A2 over magnitude A. And no surprise for the third one, we're going to use K since we're looking at the angle with the z-axis and our vector A. Uh-oh, there we go. Also a unit vector, so this time the third component will stay and the first two will disappear. So there we go. Just a way that we can get right to finding those cosine, direction cosines without having to use the dot product every time. Couple observations to notice. You'll have some homework problems that ask you about these. If you take cosine squared alpha plus cosine squared beta plus cosine squared gamma. So in other words, we're squaring A1 over magnitude A squared plus A2 over magnitude A squared plus A3 over magnitude A squared. You're going to get A1 squared plus A2 squared plus A3 squared over magnitude A squared. But notice the numerator is magnitude A squared. This is magnitude A squared. So this quotient just reduces to 1. So I get that the cosine squared alpha plus cosine squared beta plus cosine squared gamma is always going to equal 1. Also, you notice from what we did up top, A can always be kind of decomposed into the magnitude of A times a vector of those direction cosines. And if you divide over magnitude A to the other side, you might have an easier time seeing that. So AKA A over magnitude A, the unit vector in the direction of A is always going to be a vector of those direction cosines. Okay, so two good facts to know. Okay, let's try one out. Again, these don't take too long to compute, but worth trying at least one out. Find the direction cosines of A, where A is the vector 2, -4, 4, and then let's approximate the direction angles to the nearest degree. Okay, so in this case, here's my A1. I'm going to label A1, A2, A3. And so cosine of alpha is going to be my A1. Let's do the magnitude actually off to the side because we're going to need it for all three. Magnitude A is going to be 2 squared plus -4 squared plus 4 squared. 16 plus 16 is 32. 32 plus 4 is 36. Rad 36 is 6. Okay, so we're going to have A1. That's the part that points in the direction of the x-axis over the magnitude, 6. So cosine alpha is 1/3. And they asked us to approximate the angle. If you take the inverse cosine on your calculator, you get about 71 degrees. Okay, next one, beta. This is the angle made with the y-axis. Take A2, -4, divide by the magnitude, 6. So the direction cosine for beta is -2/3. Take the inverse cosine on your calculator. Make sure you're in degrees because they did ask for nearest degree. Beta is approximately, what did I get? 132. And then if you take the cosine of gamma, take the third component, the z component is 4, divided by the magnitude was 6. Cosine of gamma is 2/3, positive 2/3 this time. And so inverse cosine of both sides, inverse cosine of 2/3 is about approximately 48 degrees. Okay. So on your WebAssign, you'll have some questions like this. Okay. Wrapping up, we got a couple more topics left in this section. Next thing is what are called vector and scalar projections. I really, the easiest way to think about these is shadows. What if we were to take the shadow of one vector onto another vector? You did shadow problems in geometry if you wanted to find out the length of someone's shadow, if they're a certain distance away from a lamp or from a light post. Really same idea here, but we're doing it with vectors. So let's consider two vectors, PQ and PR, and we'll call them vector A will be PQ and vector B will be PR. And they have to have the same initial point. So notice they both start at P. If S is the foot, meaning the bottom of the perpendicular from R, okay, so that's the ending of the first vector. I'm going to outline that in red. There's the end of the first vector. If I drop a perpendicular straight down, S is what's called the foot. It's the bottom of that perpendicular. So S is the foot of the perpendicular from R to the line containing vector A, PQ. Then the vector that starts at P, where both of the vectors began, and ends at the foot of that perpendicular, this is what's called the vector projection of B onto A. So we started with vector B, and we're pushing it. Think of it as we're pushing it down. We're creating the shadow of that vector onto the other vector, PQ. So it's going to point in the same direction as PQ. And in some situations, it might be longer than PQ. And in other situations, it might be shorter than PQ. And also, I said it points in the same direction. It also could point in the opposite direction of PQ. Okay, but it's always going to form an angle of either 0 or 180 with that vector. So in our first diagram, this would be the vector projection of B onto A. Okay. And the way we notate it, we do PROJ to notate projection. Of vector B goes next to the word projection, and then the subscript is the vector that you're projecting onto. So the way I read this is the vector projection of B onto vector A. So in this case, theta, the angle between the vectors, is acute. If the angle between them is obtuse, you'll notice if you want to push B onto A, it's going to create an angle of 180 because now your foot, you're going to have to extend the vector out this way. The only way to make a perpendicular is to go the opposite way. So this would now be my vector projection of B onto A. Okay. And so the result still has to be a vector. If I want to measure the signed magnitude, how long is that vector projection? This is what we call the scalar projection of B onto A, sometimes referred to as the component of B along A. And it's the signed magnitude, could be positive or could be negative depending on which direction the vector points, but it's the signed magnitude of that vector projection. Using a little bit of trigonometry, you can see here that the cosine of theta is going to have to be the magnitude of that vector PS over the magnitude of B. And so the signed, I'm going to put signed magnitude. The signed magnitude of PS times the cosine of theta, I'm sorry, times the magnitude of B is going to equal the cosine of theta. Okay. Wrong. No. The magnitude of PS, that's going to be our component of B along A. The signed magnitude is going to be magnitude of the vector B times the cosine of theta. That's what I meant. And we're going to have another formula for this in a minute. This is just a trig way of looking at it. Right. So this right here that I'm highlighting in yellow, this is the vector projection of B onto A. If I want to know the signed magnitude, that's the component of B along A. Well, what if we don't have the angle given? What if we're just given the vectors? How do we find these vector projections and these scalar projections? Well, we use what we know. The component of B along A, so this is the scalar projection. Well, I know from the diagram on the last page, that's the magnitude of B times the cosine of the angle theta between A and B. But we have a formula for cosine of theta from earlier. This is the magnitude of B times the dot product of A and B divided by the magnitude of A times the magnitude of B. And you'll notice magnitude B cancels out in the numerator and in the denominator. So if I want to find the scalar projection of B along A, or the component of B along A, then I'm going to take the dot product and divide by the magnitude of the vector that I'm projecting onto. So I'm not dividing by magnitude of B, I'm dividing by the magnitude of A. Another way of writing this is it's the dot product of the unit vector in the direction of A and the vector B. So however you want to remember it. The vector projection has to have this size. So this is the signed, remember, this is the signed magnitude of the vector projection. So I already know the size of the projection is going to have to be that component of B along A. Okay, so this contributes the size, the magnitude. And so now that I've already taken the magnitude into consideration, I don't want to over quantify the vector's direction. So I'm not just going to multiply. I'm not going to even put a dot because I don't want to confuse this with a dot product. This is going to have to come out to a vector. If I do this, it's close, but now I'm still creating more magnitude than I want. All of the magnitude came from this first component. So really, if I want to specify the magnitude, I've already done that. Now I just have to care about the direction, which is going to make it a vector. I want to just create a unit vector since I've already done the magnitude. So I have to divide by the magnitude of A. This component is giving me a unit vector in the direction of A. And I know that has a length of 1, so I don't have to worry about giving it too much magnitude. Okay. This is how I usually go about computing it. Easiest way for me to remember it, since it really shows you how the first part deals with magnitude and the second part deals with direction. If you wanted to clean this up, you could do A dot B over magnitude A squared times A. Okay. Either way, both of these will give you the same result. Okay, so let's do it. Let's find the scalar and the vector projection of B onto A. Notationally, that means that A is going to be my subscript. First thing I would find is the scalar projection, since it's going to give you the size of the vector projection. So if we find the component of B along A, that's the scalar projection of B onto A. It's the dot product of A and B divided by the magnitude of the vector we are projecting onto. We're projecting onto A. So I want to divide by the magnitude of A. So I'm going to get, if I take the dot product, 1 times -2 plus 1 times 3 plus 2 times 1. Magnitude of A would be square root of -2 squared plus 3 squared plus 1 squared. So I get 3 on top, and I get rad 9 plus 4 plus 1. I get rad 14 on the bottom. And you can leave it unrationalized or you can rationalize it, doesn't matter. But give an exact answer. It doesn't specify for decimals, so you want to assume it's exact unless they say otherwise. Okay, now, next step, I want to know what is the vector projection of B onto A. So this one has to be a vector. Well, it's going to be the size of the projection, which we just found, 3 over rad 14. And it has to move in the direction of the vector that we're projecting onto. We're taking B and pushing it as a shadow onto A. So this has to move in the same direction as A. Might move in the same direction, might move in the opposite direction. In this case, it's going to move in the same direction since this was positive. So all I'm going to do is distribute. You could leave it like this if you want. I'm going to distribute. So I get -6 over rad 14. Oh, actually, nope. Close, but it's not quite there. My bad. Let's clean this up. It's got to be the unit vector. So the 3 over rad 14 is good. But it's got to be, right? Otherwise, we're over magnifying. So this gives me the size. This gives me the direction. So this gives me 3 over rad 14. And A was -231. And now I'm going to make it a unit vector by dividing by the magnitude, which we found was rad 14. So it's important that we make this a unit vector. Now you could either leave it like that. I am going to clean this one up since I like when the rad 14s can make the radical disappear. So I get -6 over 14, 9 over 14, 3 over 14. That works. I'm going to reduce the first fraction to -3/7. Just makes me feel better. 9 over 14, 3 over 14. That's my vector projection. So if you were sketching the diagram, here's B, here's A, here's my angle. This would be my vector projection of B onto A, given by these components. And the size of that projection, if I was to take the signed magnitude of that projection, it would have a length of 3 over rad 14. That would be the length of that green vector. That's what it means geometrically. Okay, home stretch, last part. One application you could see with this involves the concept of work. So in physics, you've probably done some work with work, LOL. The work done by a constant force in moving an object through a distance d is given by force times distance. Now, that only makes sense when the force is directed along the line of motion. So if the force is moving in the exact same direction as the object itself. But what if the force is pointing in a different direction? What if, you're pulling a wagon along the ground, but the handle of the wagon you're pulling up into the air? So maybe this blue vector PQ or PR, you're pulling the wagon's handle with a force F, some vector, but you're moving the object, the wagon, a distance d along the ground. Okay, so now you have some angle between your force vector and your displacement vector. So I want to move the wagon, say, from P to Q. That can be given by a displacement vector, which we're going to call D. So D is the displacement vector from P to Q. The work done by this force, well, it's going to be the product of the component of the force along D. So in other words, that scalar projection of F onto the displacement vector D. So it's going to be the size of this red vector projection here. And so we saw earlier that would be the vector magnitude F times the cosine of theta. So this part right here is your component of F along D, your scalar projection of F onto D, times the magnitude of the displacement vector. That's your distance. How far did you move the object? While rearranging, that's the magnitude of the force times the magnitude of the distance times the cosine of the angle between the force vector and the displacement vector. But that looks a lot like something we saw earlier. Looks a lot like magnitude A, magnitude B, cosine theta. That was just the dot product of our two vectors. So that's exactly what this is. The work done in moving an object with a force of F, a distance D, is just the dot product of the force vector and the displacement vector. Sometimes you might be given the displacement vector, in which case you can actually calculate the dot product directly with sums and products. Sometimes you might be given the angle, and you might have to actually take the magnitude of the force times the distance times the cosine of the angle between them. That's what we have going on in example 6 here. We have our friend, calculus. True person, right? You'd name your child calculus. LOL. Calculus pulls a wagon a distance of 100 meters. So I'm going to already label. There's our magnitude of the displacement vector. We're moving the wagon 100 meters along a horizontal path by a constant force of 70 newtons. Okay, so kind of set the scene here. Here's you moving the wagon along the ground. You moved it a distance of 100 meters, but you're pulling the wagon's handle at an angle of 35 degrees. So you can see that the line of motion is not moving in the same direction as your displacement. The handle of the wagon is held at an angle of 35 degrees above the horizontal. And we know the magnitude of this force vector is 70 newtons. This was meters, okay. Find the work done. Well, we have two versions we can use. We can directly compute the force vector and the displacement vector's dot product, or we can use the version involving the magnitudes. So we just have to look at the problem and decide which one's more useful. If we look at the first version, we weren't given vectors. We weren't given a force vector or a displacement vector. So I don't really know how to take the dot product directly. But I do know the magnitude of F was 70 newtons. I know the magnitude of D, the distance, was 100 meters. And I know the angle between those two vectors is 35 degrees. They told me above the horizontal. So I can compute the work with formula number 2. 70 times the displacement magnitude, the distance is 100, times the cosine of 35 degrees. If I plug that into my calculator, I get 5,734. We would be dealing with newtons times meters. You can leave it like that. If you've taken a physics class, you'll know that that is the same as measuring in joules. All right. So just one application of the dot product is work. All right. Hopefully that gets you a start on your homework. And if you got questions, don't hesitate to reach out.